Okay, so let's do 4.6 cumulative distribution functions of discrete random variables. Okay, so in 4.6 we're going to talk about the cumulative distribution functions of discrete random variables. So let's start this discussion with a definition. Okay, this is definition 4.8. The function capital F of x, which is equal to the probability that capital X is less than or equal to little x for negative infinity less than x less than infinity is the cumulative distribution function. Okay, its abbreviation is CDF. CDF, cumulative distribution function. Okay, so that function is a cumulative distribution function. Capital F of x, capital F of little x is equal to probability that capital X is less than or equal to little x. So just to emphasize this is little x and this is little x. That is going here. That's different than this one. This is capital X. This is the discrete random variable, capital X. And capital F of little x is the probability that your discrete random variable is at most the value of little x. Okay, so let's look at an example. Example 4.20. Finding the cumulative distribution function. So finding the cumulative distribution function, let capital X be a discrete random variable whose only positive values are -1, 2, and 5. Suppose the probability function of capital X is f of x is equal to 1/4 for x equals -1, 1/2 for x equals 2, and 1/4 for x equals 5. Okay, and so the goal is going to be to find the cumulative distribution function of x. Okay, so we want to find the cumulative distribution function of x. That's the goal. Okay, so that's the cumulative distribution function, right? And this is the equation for it. So capital F of x, of little x, is equal to the probability that capital X is less than or equal to little x. And that's equal to, well, if x is less than -1. If little x is less than -1, if little x is less than this -1, and the value capital X are only it says this was only positive values are -1, 2, and 5, right? And the respective probabilities of capital X being those values are 1/4, 1/2, and 1/4. then if little x is less than -1, the probability that capital X is at most a number less than -1 is 0. Because the smallest value of little x is -1. And so if capital X is at most something less than -1, the probability of that is 0. So capital F of little x is 0 if little x is less than 1. Capital F of x, which is still equal to the probability of capital X equaling to little x, less than little x. Now, if -1 is less than or equal to x, strictly less than 2, then little x is a number greater than or equal to -1, but less than 2. The probability of that is 1/4. Because the only value that x can take in this interval that has non-zero probability is x equals -1. It does not include 2. And so when capital X is -1, the probability is 1/4. When it's any other value here, it's 0. Right? If it's 0, the probability that capital X is equal to 0 is 0. Probability that capital X equals 1 is 0. Probability capital X equals -1 is 1/4. I mean, if the value of little x is large enough so it includes those values. Okay, the capital F of x, which is the probability that capital X is less than or equal to little x, is equal to, now if 2 is less than or equal to x strictly less than 5, then the cumulative distribution function, capital F of x, is equal to 3/4. And so the reason for that is because, let's say for instance, little x is equal to 3, right? What is the probability that capital X is at most 3? Well, it could either be -1 or 2. The probability of -1 is 1/4. The probability x equals 2 is 1/2. So you add those two probabilities, 3/4. The probability capital X is at most 3 is 1/4 plus 1/2, 3/4. And then the last value to consider, well, I guess is the probability that capital X is at most little x here if 2 is less than or equal, if x is greater than or equal to 2, and if x is greater than or equal to 5, or 5 less than or equal to x, then the probability is the sum of those, which is 1. Okay, and so now we found the cumulative distribution function of x from there. So our conclusion, this example right here, the conclusion is that for -infinity less than x less than infinity, we get that capital F of x is equal to 0 for x less than -1, 1/4, when -1 is less than or equal to x, so strictly less than 2, 3/4 for 2 less than or equal to x, strictly less than 5, and 1 for x greater than or equal to 5. Good, so capital F of x is that. It's a cumulative distribution function. Sorry, okay, that's the other way. Okay, so then that's the conclusion. Let me add here before, I'm going to write something at the top here that has to do with this. And I'm going to erase the whole board. There's something else I want to add. Let's say we graph this function, capital F of x. Okay, so when we'll graph is y equals capital F of x, and so the x-axis, this is going to be the x-axis, and this is going to be y equals capital F of x axis. And so here's the, this is the value 1/4, 1/2, 3/4, and 1. -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay, so then here, capital F of x is 0 if x is less than -1. And it's 1/4 if -1 is less than x less than 2 from here. It's 3/4 if 2 is less than or equal to x less than 5. And it's 1 for x greater than or equal to 5. Okay, and so this is y equals capital F of x. That's the graph of the cumulative distribution function we found, right? And so this is what this is illustrating is that the probability that capital X is at most these values is 0. But then when you reach -1, the probability that capital X is at most -1 is 1/4. And then as you continue, the probability that capital X is at most these values is still 1/4. Then when you reach 2, when you get to 2, it now jumps to 3/4. So the probability that capital X is at most 3/4, at most 2, sorry, is 3/4. Continue, stays 3/4, and the probability that x is at most 5 is 1. And then x gets larger. Well, probably x is at most these x values is 1. The probably capital X is at most these little x values is 1 for little x greater than 5. Okay, and so that's the graph of the cumulative distribution function of x in example 4.20. Okay. Okay, so I can erase this. Alternate definition of the cumulative distribution function of the CDF, which is cumulative distribution function of a discrete random variable. Okay, so alternate definition of the cumulative distribution function of a discrete random variable. Let f be the probability function of the discrete random variable capital X. The function capital F of x is equal to the sum over t less than or equal to little x of f of t for -infinity less than x less than infinity. Is the cumulative distribution function, which I'm going to abbreviate CDF, is the CDF of capital X. The sum is over all possible values of t less than or equal to x for which f of t is defined. Okay, so this is another way to define the cumulative distribution function. Let little f be the probability function of the discrete random variable capital X. The function capital F of x, which is equal to the sum of f of t over t less than or equal to x for any real number x, is the CDF of x. The sum is over all possible values of t less than or equal to x for which f of t is defined. So we're adding up the values of f of t where t is at most x and where t is in the domain of f. Okay. And it's a summation here because we're talking about a discrete random variable capital X, right? So its sample size is either finite or the values that capital X can take is either either finite or countably infinite. Okay, so we can use the summation symbol there. Okay. Later we'll define this for a continuous random variable. Right now we're talking about discrete random variables, and so this summation will be changed to an integral. But right now we're talking about discrete random variable And the cumulative distribution function uses a summation symbol because the possible values of capital X are the finite or countably infinite. It's a discrete set. Okay. Example 4.21, finding the probability with the cumulative distribution function CDF with the CDF. Okay, so we're going to have a cumulative distribution function, and we want to find the certain probabilities using it. Okay, so let capital X be a discrete random variable whose cumulative distribution function, whose CDF is capital F of X, which is equal to 0 for X less or equal to -3, 1/6 for -3 less than or equal to X strictly less than 6, 1/2 for 6 less than or equal to X strictly less than 10, and 1 for 10 less than or equal to X. Okay, so let capital X be a discrete random variable whose cumulative distribution function is that function. And so let's find the following. Part A, find the probability that capital X is at most 4, is less than or equal to 4. The probability that -5 is strictly less than X, less than or equal to 4. The probability that X is equal to 3, -3. And the probability that X is equal to 4. Okay? Okay, so we have the cumulative distribution function here. So the probability that X is at most 4, right, that's equal to capital F of 4, right? That's what the meaning of capital F of 4 is. Capital F of 4 is the probability that your discrete random variable capital X is at most 4. And so capital F of 4 is, well, if the input for the capital F is between -3 and 6, including -3, not including 6, that's 4. 4 is in there, and the capital F of 4 is 1/6. Okay, and so that's the answer to that one. Now, what is the probability that -5 is less than X, less than or equal to 4, using that function? Well, it's the probability that X is at most 4, and it's greater than -5. So you can think of this as the probability that X is at most 4 minus the probability, it's equals there, minus the probability it's at most -5. Right, so what this is saying is that X is less than or equal to 4 and greater than 5. Well, equivalently, it's less than or equal to 4 and not less than or equal to 5. So if X is less than or equal to 4, I'm saying it's less than 4, but instead of saying it's greater than -5, I want to say it's not less than or equal to -5. And so I'm just going to subtract the probability that X is less than or equal to -5. Okay, and so again, prime probability that -5 is less than X, less than -4, it's equal to the probability that X is at most 4 minus the probability that X is at most 5. Because this is saying that X is at most 4 and not at most -5. Okay, and so what is P of X of -4? That's capital F of 4 minus P of X less than or equal to -5. That's P of -5. I mean, that's capital F of -5. And so what's capital F of 4? It's 1/6. And what's capital F of -5? It's 0. So 1/6 minus 0 is 1/6. So that probability is 1/6. Now, P of X equals -3. What is the probability that X is equal to -3? Sorry, wait. This is a strictly less than sign here. fix it. That's strictly less than. It does not affect anything I did to this point. Okay. The probability that x is equal to -3. Well, when x is less than -3, capital F of x is 0. Once x reaches -3, the cumulative probability distribution function jumps to 1/6. That means at x equals -3, the probability was 1/6. That's equal to 1/6. Okay? And then probably x is equal to 4. What is that equal to? Well, the probability x is equal to 4. 4 is here. And so the cumulative distribution function is at -3 is 1/6. And then it can stay as 1/6 until we almost get to x equals little x equals 6. When x is 4, it's in this interval, and the cumulative probability doesn't change. So the probability x equals 4 is 0. Okay? If the probability of x equals 4 was some positive number, then that would mean that adding up these probabilities, if it was already 1/6, it would have to become larger, right? But including the value of x equals 4 in this interval does not increase the value of capital F of x, which means that since you're adding up probabilities here, the probability that capital X equals 4 must be 0. Okay? And so that solves part A. Okay, so let's go to part B. Part B is find the probability function of f. Of capital X. Sorry, find the probability function of capital X. So that's f of x, which is probably capital X equals little x. That's equal to, well, the jump here is at x equals -3. And so the probability is 1/6 if x is equal to -3. That's the first jump. The next jump is at x equals 6. And that jump, it's not going to be 1/2. It's going to be the increase in probability from 1/6 to 1/2. So 1/2 is 3/6. So it's going from 1/6 to 3/6. So the jump is 2/6. That's 1/3. And so the probability is 1/3 if x is equal to 6. So when x is equal to 6, it jumps from 1/6 to 1/2. You add 2/6 to 1/6 and you get 1/2. When x is 10, it jumps from 1/2 to 1. So it has a probability of 1/2 if x is equal to 10. And that's it. Those are the only values of, those are only values of capital X that have non-zero probability. And if you add it up, you can see that's 3/6, 2/6, 1/6. That adds up to 6/6, which is 1. And so that's the probability function of capital X. That piecewise function. Okay, and so that's the end of example 4.2.1, and that's also the end of chapter 4. Okay. Okay, so good. Chapter 4. Let's keep going. Chapter 5. Continuous random variables. And probability density functions. So continuous random variables and probability density functions. 5.1 Introduction. Okay, so when the set of possible values of a random phenomenon is is a continuous extent of real numbers the value of the random phenomenon is a continuous random variable. Okay, so introduction to continuous random variables and probability density functions, 5.1. When the set of possible values of a random phenomenon is a continuous extent of real numbers, the value of the random phenomenon is a continuous random variable. So let me give you an example of this. For instance, let's say you have a dartboard, and let's say you have the target at the middle, right? And so here's a dartboard. Okay, and so you have a dart, and you stand a few feet away from it, and you try to throw it at the very center, right? And so let's say capital X is the distance from the center. So it's distance from the center. The dart hits the board. Okay. Well, so one way you could measure it is just by, we could even say inches. So let's say capital X is the distance from the center. The dart hits the board in inches, right? But we're not rounding to the, let's say we don't round to the nearest inch, right? And so that means you could have a part of an inch, right? So you don't necessarily hit the dartboard in just 1 inch or 2 inches or 3 inches away or 0 inches away. You could hit the target 1.37582 inches away from the center of the dartboard, okay? And so the capital X takes on real values, right? From 0 up to whatever number you want. And so capital X here is a continuous extension of the real numbers. Okay, so capital X here is a continuous random variable. Okay, and so that's an example of a continuous random variable. Now, if we rounded the number to the nearest inch, if I said, if capital X was the distance from the center of the dartboard where I round to the nearest inch, then it would be a discrete random variable because the values capital X could take could only be 0, 1, 2, 3, 4, 5, 6, and so on. It could even be, there could be infinitely many, but it would still be a discrete random variable, right? So it's not just infinite that makes it discrete or continuous. Just infinite alone doesn't make it continuous random variable. You can have have capital X attain infinitely many values but still be discrete, okay? But you can see how the distance from the center of the board that the dart hits, capital X is the distance, you can see how, right, we're thinking of real numbers here, of real number distance, right? We're not thinking of integer distances, we're not non-negative integer distances like 0, 1, 2, 3, 4. That would be a discrete random variable, right? Rounding to nearest inch. If we don't round to nearest inch, again, this is a continuous random variable. Okay, so that's an introduction to what a continuous random variable is. And so now let's study it on a deeper level. Okay, so now this is 5.2, probability density functions. Okay, so 5.2 probability density functions. The probability function, f of x, which equals to the probability that capital X equals little x, plays an important role in a discrete random variable x. Okay, so I'm going to get to the part where it's continuous. Okay, so let's think of the same. Let's think of a discrete random variable still, and f of x is equal to probably capital X equals little x. And so let's think of that target situation again, right? And so here's the target and the dartboard. The origin is where is the target, and capital X is the inches from the center. Capital X is the number of inches the dart is away from the target. Okay? But then let's round capital X to the nearest, in part A, let's round it to the nearest inch. Okay? So capital X is going to be a discrete random variable, which is the number of inches the dart hits the board away from the target, rounded to the nearest inch. That will make it a discrete random variable because it can only, because it only takes on a discrete is only so the sample space is discrete. It's not next to the discrete. Okay, so then 0, 1, 2, 3, 4, 5, 6, dot, dot, dot. Oh, a little bit more here. 7, 8, 9, 10, dot, dot, dot. And so let's just draw this thing. Okay, good. So, so this is a probability histogram. This is a probability histogram for this situation. That there's a certain probability that it's 0 inches away. There's more likely it's 1 inch away. A little bit less likely it's 2 inches away, and so on. It's rounded to the nearest inch, right? And then once you get to 10, you're saying it's 0 chance you're gonna be that far off. Okay. Now let's say part B. Instead of rounding the distance to the nearest inch, let's round it to the nearest half inch. Okay, now let's take the probability histogram when it's half an inch. And so it's half an inch, you get, let me put the numbers here. 0 is 1. Okay, and so now okay, so actually, okay, so if it's 0 inch, and then let's say there's a half. So we have the half values here: 3 halves, 5 halves, 7 halves, 9 halves, 11 halves, 13 halves, and so on. Okay, and so now this thing is going to, let's say, okay, so now let's say that's the half-inch histogram, where you look at the probability that it's 0 inches away, half an inch away, 1 inch away, and so on. And then for part C, let's take the limit of the probability histogram. Okay, so let's take the limit of the probability histogram. Let's find, well, if we rounded to the nearest 1 over n inches, where n is 1, 2, 3, 4, and so forth, let's take the limit as n approaches infinity of that. So, actually 1 over 2 to the n. Let's keep halving it. So it's 1 inch, half an inch, a quarter inch, an eighth an inch, and so forth, until you're rounding it to, you keep rounding it to its smaller and smaller amount, fraction of an inch. Okay, so you take the limit of that, and you get this curve. Okay, this is the limit and so on. So this is the limit of the probability histogram, right? So you take the limit of that and you get this. Okay, and so this curve is called the probability density curve of the random variable x. This is called the probability density curve of the random variable x. Okay, and it's the limit of the histograms corresponding to the corresponding discrete random variables. So it's the limit of these histograms. Okay, so that's the probability density curve, and so that's the probability density curve. It's the limit of these histograms. Okay. Right, so there's so this is the histogram of the discrete random variable where you round it to the nearest inch. This is the histogram of the discrete random variable you round it to a half an inch. And so as you keep making them smaller, you're getting histograms for other discrete random variables. And so we're taking the limit of these probability histograms, and so we're taking the limit of histograms of corresponding discrete random variables, one for each situation. Okay, so that's the probability density curve. And so from that curve, we get a function. So let me write that function. I'm going to erase A and B. I'm going to keep C, because we're looking at that right now. Okay. And so C is the limit of probability histograms. And so the function defined by that curve, so the function defined by the probability density curve is the probability density function of capital X. And so that function is this function. Probably that little a is less or equal to capital X less or equal to little b is equal to the definite integral from a to b of little f of x dx. And the probability that capital X is less or equal to little x is equal to the probability that negative infinity is less than x, less than capital X, less or equal to little x. And that's equal to the integral from negative infinity to little x of f of t dt. Here t is a dummy variable. Okay, so the function defined by the probability density curve, that one, is the probability density function of x. Okay, so here's the probability. F of x is not the probability that your variable x equals that little x. So for instance, if I did 1 here and I took little f of 1, that would be the height of this curve, right? That would be little f of 1. So you have to think a little bit. You have to kind of be flexible with what you were thinking for what you thought previously. So here's 1. F of 1 is the height of that probability density curve at x equals 1. But that's not the probability that x equals 1. Okay? The probability that x equals 1 is not f of 1. It's not the height of that curve. Okay? Here we're talking about the probability that x takes on a range of values. And if you want the probability that x takes on a range of values, you integrate that function from a to b. So for instance, I wouldn't talk about I would not say the probability that f of 1 is the height of this curve. Instead, I would say, well, what's the probability that capital X is between 1 and 2? Then I would look at the area of that, and where this is y equals f of x, the height of this graph. That's this little f here. But the probability that it's between a range of values would be integrating this function. Then you'd find the probability that capital X takes on a range of values. If you look at any one particular value, though, the probability is 0. Okay? And so when you take a continuous range of values, you're going to get a probability possibly with this by integrating. But if you look at any one particular value of x, it's 0. Right? And so again, going to the dartboard to make sense of why the probability would be 0. Right? If here's the center, here's your target, right? And capital X was the distance that your dart hit away, the distance between where your dart hit the center of the board. If that was the value of capital X, right? To say that you want to know the probability that it was exactly 1 inch away from the center. But if you think in real life, would you really be able to hit that target exactly 1 inch away? And so we're saying no. I mean, it could happen, but we're saying its probability is 0, right? So again, saying the probability of an event is 0 does not mean it can't happen, and saying the probability of an event is 1 doesn't mean it's certain to happen. And so it's certainly possible you could hit the dart 1 inch away from the center, but we're saying the probability of that is 0. And what that means is that it's almost certain to not happen, okay? So we're pretty sure, we're very confident, it probably won't happen. That's what a probability of 0 really means, okay? A probability of 0 really means it's probably not going to happen. Like, it wouldn't make sense to think that it could happen. It's that unlikely and that difficult. It's almost certain to not happen, okay? So it's almost certain that you will not hit the dartboard exactly 1 inch away from the center. And so it has a probability of 0. And so if you take one particular value of this variable and say, I want to know the probability that I am exactly that distance away from the target, a mathematician will say the probability is 0. I'm almost certain that won't happen. Okay? So mathematicians will say, I'm going to give the probability of 0 to you hitting it exactly any fixed distance away from the center. It could happen, but we're almost certain it won't. Now, if you take a range of values, if I say, instead of saying it's going to be exactly 1 inch away from the center, if instead the question is posed, what is the probability or the likelihood that you hit the target somewhere between 1 and 2 inches away from the target, then a mathematician says, I can tell you that has a positive probability. There's a chance you'll hit that target between 1 and 2 inches away from the center. That's possible. That could happen, and it'll be a probability. But to say that you'll hit the target exactly some fixed distance away, and a mathematician would say, I'm almost certain that won't happen. So it's going to have a probability of 0. It could happen, but it probably won't. That's what probability of 0 means. Okay? Okay. Okay. Right? Because your intuition tells you, well, it can't be probability 0. It's possible you could hit it at some fixed distance. And the counter to that is that you don't understand what probability of 0 means. Probability of 0 does not mean something can't happen. It just means you're almost certain it won't. Okay? So here, again, is the probability of a range of x values, and the probability that x is at most some little x value. All right? And so this is going to be capital F of x. capital F of little x. That's going to be that. So this is going to be this is the cumulative distribution function. This is just the probability that x takes on a range of values. Okay. Okay, so let's look at an example. So consider the experiment. Consider the experiment of selecting a number from the interval 2, 4, not including 2 or 4, not including the endpoints of the interval. Assume if subintervals I sub 1 and I sub 2 of 2, 4 are equal in length, the probability of the number being either interval is the same. Being in either interval is the same. Let capital X be the number selected. Then f of x is equal to 1/2 for 2 less than x less than 4 and 0 elsewhere. Okay, so we have a continuous random variable here again. So consider the experiment of selecting a number from that open interval 2, 4. Assume if subintervals I1 and I2 of that interval are equal in length, the probability of the number being in either interval is the same. Let capital X equal the number selected, then the probability function of x is this: 1/2 if x is in the interval, for x being some fixed number in the interval, 0 elsewhere. Okay, and so you can show this by saying what is the probability right, so what is the probability that okay, so the probability that 2 is less than x less than 4 is going to be the interval from 2 to 4 of f of t dt. So let's say that, but now the probability of that is going to be, well, so you can only select a number from 2 to 4, and so that has to be 1, right? And so if the subintervals are equal in length, the probability of the number being is the same. So that means f of t is going to be constant. So this is the integral from 2 to 4 of a constant dt. And so that's a constant times 4 minus 2. That's 2c. So what we're saying is 2 times that constant is 1. And that implies that the constant is 1/2. And so that implies that f of t is equal to 1, f of x is 1/2 when for 2 less than x less than 4. Okay. Okay, so 5.3, continuous random variables. Okay, so 5.3, continuous random variables. Definition 5.1. So definition 5.1, a real valued function capital X defined on a sample space capital S with probability set function capital P is a continuous random variable provided there is an integrable function f such that the probability that x, capital X is most little x, is equal to the integral from negative infinity to little x of f of t dt for negative infinity less than x less than infinity. The function f, the function little f, is a probability density function of the random variable x. Okay, so definition 5.1 is a definition of a continuous random variable, a real value function capital X defined on a sample space capital S with probability set function capital P is a continuous random variable provided there is an integrable function little f such that the probability that capital X is of most little x is the integral from negative infinity to x little x of f of t dt for any real value of real value of little x. The function f is a probability density function of the random variable capital X. Okay? This is kind of like the situation we had with the limit of the histograms, where we had this was the limit of the histograms, and the graph here was the graph of the probability density function f. And then we use that f here, we use that f to find probabilities that capital X was in an interval of values, right, from a to b, by integrating from a to b f of t dt. And so if you can do that, or instead of saying from a to b, it would just be from negative infinity to b, right? So you'd be integrating. In that case, it would be 0 to b because there's nothing there. But as far left as you can go to some given little x, in this problem it's little x. And so if you integrate from negative infinity to x, and you sum up all the values of this probability density function up to including x, if you can do that, then you have a continuous random variable. Okay, this f has to be integrable. That's mentioned here. This f, it has to be an integral function f. Okay, so that's the definition. Let's keep going. 5.4. So 5.4 is finding probabilities. for continuous random variables. Okay, finding probabilities for continuous random variables. Okay. Good. Let's check to make sure you can see what I'm writing. 1, the probability that capital X is equal to little x is 0 for negative infinity less than x less than infinity. 2, the probability capital X is less than little x is equal to the probability that capital X is less than or equal to little x, which equals the integral from negative infinity to little x of f of t dt. This is for any real x. Okay, so 3, probability that a is less than or equal to x less than or equal to b. That's equal to the probability that a is less than or equal to x strictly less than b. That's equal to the probability that a is less than x less than or equal to b. That's equal to the probability that a is less than x less than b. Okay, so you either include or not include the equal sign for either inequality, right? Because the probability that x equals any single value is 0 for a continuous random variable. Discrete random variables, capital X has a positive probability of taking on particular values. But for a continuous random variable, the probability that you would say capital X equal to anything would be 0. Okay? So you can either include or not include x, a, and b on either side, and the probability is the same. That's because of 1. And all 4 of those probabilities are equal to the integral from a to b of f of t dt for a less than b. Right? So a has to be less than b. Right? We're talking about integral. If a was equal to b, it would just be one value of x, and the probability would be 0. But if you thought of it as an integral anyway, it would still be 0, but it would be overkill. Right? So why define it for a equal to b? You would just think of it as case 1. Okay, so then that's part 3. So observe the probability of a less than x less than or equal to b is equal to the probability that x is less than or equal to b minus the probability of x is less than or equal to a. So I did that in an earlier problem. And that is equal to the integral from negative infinity to b of f of t dt minus the integral from negative infinity to a of f of t dt. And through rules of integrals in calculus, this is the integral from a to b of f of t dt, which is what it should be. Okay, so we're seeing how this is equal to that minus that. That's because this x is at most b and not at most a is greater than a. So x is at most b and not at most a. So it's the probability that x is at most b minus the probability that x is at most a. And you still get this integral which defines that, and this minus this is also that. Okay, another thing to observe, that the limit as c approaches 0, the probability of x minus c is less than capital X, less than x, this is little x, is equal to the limit as c approaches 0 of the integral from x minus c to x of f of t dt, and that is equal to 0, and that implies that the probability that x is equal to little x is 0. Okay, so this is just proving 1. I have to prove that. So let me just say it again. So observe that the limit as c approaches 0 of the probability of x minus c, little x minus c less than capital X less than c, that's the limit as c approaches 0 of the integral representing that probability. The integral from x minus c to x of f of t dt, Well, you take the limit as c approaches 0, then the lower limit and the upper limit of that integral become the same. And so that means that equals 0. And so what that means is that you take the limit as c approaches 0 of this, so this is less than or equal to, sorry. That's less than or equal to there. That's less than or equal to, so there. So that means that the only capital X value that you're considering when you take the limit as c approaches infinity of this, the only value of capital X you can consider is it equaling little x. And so this shows you that the probability that capital X stays in this interval as c approaches 0, there's only one capital X that can do that. As c gets arbitrarily small, x minus c gets arbitrarily close to x. And so if x minus c is getting closer and closer to little x, that means that no matter what other value of capital X you chose other than little x, like little x minus 1 millionth, I could choose an appropriately small value of c, and then x minus c less than x, less than little x, less than or equal to little x, that would not include little x minus 1 millionth. Okay? And so as c gets closer and closer to 0, x minus c and x get closer and closer to each other, and the only value of capital X that stays in that interval is little x. And so that means that the probability of capital X equals little x is 0, because that limit of that probability is 0. And so that proves that the probability of capital X equals little x is 0. And that's for any value of little x, any real number little x you can choose there. Because you're doing little x minus c, and the limit of c, you're taking the limit of c approaches 0. Okay, so that proves 1. Okay, so we won't prove 2 and 3, but we proved 1. Okay, let's keep going. So example 5.2. Let capital X be a continuous random variable with probability density function f of x is equal to 2x for 0 less than x less than 1 and 0 elsewhere. So let capital X be a continuous random variable with probability density function f of x equals 2x for 0 less than x than 1 and 0 elsewhere. So find the probability that capital X is at most 0.4. The probability that x is greater than 0.2. Probability that 0.2 is less than x less than 0.4. The probability of x equals 0.5. Probably x is less than 0.4. Okay, so let's find these 5 probabilities. For example, 5.2. So the probability that x is at most 0.4. That's equal to the integral from negative infinity to 0.4 of f of t dt. T is the time variable here. So that's equal to the integral from negative infinity to 0.4 of 2t dt. That's equal to t squared. That's right. So the way you compute a improper limit would say taking the limit as capital M approaches negative infinity of the differential from capital M to 0.4 of 2t dt. And that's equal to, well, an antiderivative of 2t is t squared. And so we're just going to take the limit as capital M approaches negative infinity of t squared evaluated from capital M to 0.4. And so that's equal to the limit as capital M approaches negative infinity of 0.4 squared minus capital M squared. So that's equal to the limit as capital M approaches negative infinity of 0.16 minus M squared oh, sorry. Okay. I don't need to do this. I made a mistake. Okay, so then okay, so it's 0 elsewhere, so it's only between 0 and 1 where it's like this. So this is the integral from negative infinity to 0 to t dt of all right, so then this is the integral from negative infinity to 0 of f of t dt plus the integral from 0 to 4. So the integral from negative infinity to 0 of 0 dt plus the integral from 0 to 0.4 of f of t dt, which is 2t dt, right? So it's 0. It's 0 everywhere less than or equal to 0. So it's 0 there. This is equal to the integral of 0 over 0, 0 plus t squared evaluated from 0 to 0.4. And so this is equal to 0.4 squared minus 0 squared, that's 0.16. Okay. All right, so the probability x is at most 0.4 is 0.16. Okay, so that's that one. Okay, keep going. So we did the first one. Now done the first one. And that one is done. Now the probability that x is greater than 0.2 is 1 minus the probability that x is less than or equal to 0.2. And so this is 1 minus the integral from negative infinity to 0.2 of f of t dt. But this is equal to 1 minus the integral from negative infinity to 0 of f of t dt minus the integral from 0 to 0.2 of f of t dt. Right, so remember the from negative infinity to 0, f of t is 0, and it's 2t in the other integral. So this is equal to the 1 minus the integral from negative infinity to 0 of 0 dt minus the integral from 0 to 0.2 of 2t dt. And so that's 0 minus t squared evaluated from 0 to 0.2, and that's equal to the negative of 0.2 squared minus 0 squared. And so that's 0.4, the negative of, well, 0.04. This is negative 0.04. Oh, sorry. 1 minus that. So it's equal to 1 minus that. And so it's 1 minus 0.04, which is 0.96. Okay. Okay, that's the second one done. Okay, probability that 0.2 is less than x less than 0.4. Let's explain it a little simpler. This is 0.2, integral from 0.2 to 0.4 of f of t dt. That's equal to integral from 0.2 to 0.4 of 2t dt. That's equal to t squared evaluated from 0.2 to 0.4 by the fundamental theorem of calculus. That's 0.4 squared minus 0.2 squared. That's equal to 0.16 minus 0.04. That's 0.12. That's 0.12. So that's 0.12. The probability that x equals 0.5 is 0. Right? The probability that x equaling any particular value when x is a continuous random variable is 0. And the probability that x is less than 0.4, that's equal to 1. That's equal to the probability that x is less than or equal to 0.4. That's equal to the integral from 0 to 0.4, because it's 0 everywhere less than the probability density function f is 0 when x is less than or equal to 0. And so this is 2t dt here. And so this is t squared valued from 0 to 0.4. and this is 0.4 squared minus 0 squared. That's 0.16. Okay, and so that's the solution to probably x less than 4. Probably x less than 4 is equal to probably x less than 0.4, and we got that to 0.16 already. Okay, and so we'll stop there, and the next video will continue.